Okay, all right. Well, good morning. Happy Wednesday. It, we're in week 8. We got like a week and a half left of school. Is that about it? Another 2 weeks, 2.5 weeks. I don't know. How does this work? So we got half of this week, week 9, week 10. I guess 2.5 weeks of school, finals. That's it. That's it. Okay. All right. Today we'll take a look at clustering. Um, Clustering falls under unsupervised learning. So everything we've done so far has been supervised learning, and this is unsupervised learning. And so there's kind of like, oh well, first of all, what's the difference between supervised and unsupervised learning? Okay, supervised learning means there are answers, and you can evaluate how well you're doing by comparing your answers to the true answers. Okay, so it's kind of like getting a practice test, all right? And you can say like, have I learned the material well? Well, let's try taking the practice test. And if you score 100% on the practice test, you go, yes, I've done a great job studying, right? And but I mean, it's also possible that you've learned too much specifically for this practice test, right? That's overfitting. But basically, supervised learning says there are target values that we're trying to predict, and we are able to measure how far we're off from the target values, right? We have a loss function that says you're very close to the target values, or you're really far from the target values, so you have to do better, okay? Unsupervised learning, there's no target values, okay? And instead, you have to kind of just search for structure with just the input variables itself. And, you don't know if you're doing a great job or not, right? It's kind of just like when the professor just says, all right, study for the exam. Well, what should we study? Everything. And then you go, okay, well, I hope I'm learning the right stuff. so that's unsupervised, okay? So there's parallels to like your learning and machine learning, but yeah, unsupervised learning, we don't have target values, and we're just like, okay, put these things, put similar observations together, okay? So clustering is a kind of a common application of unsupervised learning, and it's just kind of like, okay, find things that are similar to each other, like group movies that are similar to each other, so like when you're on Netflix and you like this one show or this one movie and it gives you recommendations, like we want those recommendations to be good, right? If you like, or Spotify or whatever, all of these things, it's like you like this artist and then it says, hey, why don't you check out these things? And people respond to the quality of those recommendations. If it makes good recommendations, they're more likely to use the service. But there's no answer that says like, I don't know, like who's an artist similar to Taylor Swift, and how do you say put things that are similar, right? And for as far as like musical taste, you probably wouldn't put someone people of different styles together or something, or I don't know, but anyway, that's an application. It's kind of tough, and then there's another method of unsupervised learning is dimension reduction. How do you kind of reduce the number of variables that you're dealing with? We'll take a look at clustering today. Clustering is to kind of group objects so that objects within a group are similar to each other, and objects in different groups are not similar. How do we define similarity? There's there's lots of ways. We're going to look at kind of one of the simplest ways, which is just measuring Euclidean distance. That means you kind of need numeric variables. If you have categorical variables, then then you can't really measure Euclidean distance. What's the Euclidean distance between the color red and the color green? Doesn't quite work out, right? So that's a problem with some of these clustering algorithms. Is like, how do you cluster categorical variables? That's like a whole different thing, and beyond the scope of our course, I'll say. So grouping similar products, grouping similar documents, or physical locations. Physical locations is real easy. I mean, not real easy, but because you can just graph them like on a 2D map and say, okay, these are really close together. And it only gets like wonky if you're like near the poles, but nobody lives in Antarctica. I mean, not no one, but we don't have to worry about rideshare pickups in Antarctica. So, but other things, the idea of kind of grouping things together is interesting. All right, we're going to look at kind of one of the most basic, yet still one of the most useful clustering algorithms, and that is k-means clustering. Okay, k-means clustering says we're going to use Euclidean distance to measure how similar objects are to one another. One thing is k-means clustering. It starts with a k, and I don't know, for whatever reason, because it starts with a k, sometimes it gets mixed up with k nearest neighbors, but they're not similar at all. Okay, k-means is unsupervised learning. K nearest neighbors is supervised classification. So they're very different. And in k-means clustering, the clusters are defined by centroids, or basically just means is what it is. The centroid is the mean of all the points that are assigned to a particular cluster. This is the formula for getting the centroid of cluster K. The mean of cluster K is this formula. It looks more complicated than it actually is. Basically, it's just take the points that belong to K, add them up, and divide by how many points belong to cluster K. And so basically you have this variable z, which is an indicator variable, either a 0 or a 1. And so if it belongs to cluster K, this z for observation n is going to be a 1. And if it doesn't belong to cluster K, it's going to be a 0. So the sum of the z's is going to be how many observations belong to cluster K. And then when you multiply the z's times the x's, only the x's that do belong to cluster K get added together. So it's just calculate the mean, right? Add up the points, divide by how many you have, but it's just for the ones that belong to cluster K. So that's what this is. Okay, and this is the algorithm for k-means clustering. This uses this is the random partition method, and technically, I guess this is the naive k-means clustering algorithm. But this is how it works. So the first thing you have to do is you have to define how many clusters you're going to search for. So that's step 0. That's you have to pick that yourself. Okay, and then for the random partition, what we do is we just randomly assign all of the points to the clusters, to each of the clusters. So you say, okay, here's your first point. And let's say we're searching for 3 clusters. You're going to just say, okay, I randomly assign you to 1, 2, or 3. Okay, second point, randomly assign you to 1, 2, or 3. Next point, randomly assign you to 1, 2, or 3. You do this for all of the points. And then so once all the values are assigned to a cluster, then you calculate the centroid of each cluster. So you say, okay, let's look at all the points assigned to cluster 1. What's the centroid? Well, all the points assigned to cluster 2. What's the centroid? And so on. And then so you'll end up getting k different centroids. So in our case, if we have three clusters, we'll have 3 centroids. And then you reassign all the values to a cluster by associating the value to the centroid, to the nearest centroid. So you measure the distance from each point to the k different centroids, and you say, okay, which one is the closest one? And it gets assigned there. And then you iterate, okay? You iterate between recalculating the centroids and then reassigning points. So it goes just between recalculate, reassign, recalculate centroids, reassign points, recalculate centroids, reassign points, and until you reach some kind of convergence. There is an alternative initialization method. This is called the 4G method, named after a person. And that one just says, instead of randomly assigning your points to a cluster, just randomly select k values in your data and use those as your initial clusters, initial centroids. And then you, again, once you have these initial centroid locations, you reassign points to the nearest centroid, and then you recalculate the centroids, and then you reassign, recalculate, reassign. Okay? When you do random partition method, the initial clusters, the initial centroids end up being kind of near the center of all of the points. They're not going to be exactly the same because of random assignment, but they end up kind of being close to each other. Whereas if you use the 4G method, they're a little bit more spread out. Clusters are assigned using Euclidean distance, so it's recommended to scale or normalize all of your values so they're of similar magnitude. Okay, if you don't do this, then if one of your variables has kind of much greater magnitude or much greater variance than the other variables, then your cluster assignments are going to be dominated by that one variable, right? So, if you look at, say, like, you're going to cluster people together by their height and their weight, okay? It's human height, if you measure in inches, probably, your shortest person and your tallest person probably won't vary much more than, say, 24 inches. Okay, that's going to be like the max range. Not the max, but like, you probably won't have much more than 24 inches of range for height in inches. But then for difference in weights, you might have a difference of like 150 to 200 pounds in terms of range of weights. Okay, and so with Euclidean distance, it's going to look at the range of weights, and that's going to be the variable that dominates everything. So if you kind of turn everything into z-scores, that will kind of reduce that issue. Okay, let me go ahead and give you your first view quiz answer for today, which is the letter A. A as an apple. Okay, let's just take a quick look at an example. All right, so here are 8 data points, and we're going to say, well, let's look for 2 clusters. Okay, so this is the easiest. We can look at it, and we can figure out 2 clusters just easily looking at it. But we'll go ahead and use the algorithm and see what happens. But yeah, and obviously, clustering in 2 dimensions is reasonably easy for us to do as humans because, like, we're really good at seeing things in 2 dimensions. Even maybe kind of 3 dimensions, if you can kind of plot it in 3 dimensions, we're good at seeing stuff. But then again, once you get into higher dimensional settings, it becomes a lot harder to for a human to do the job. But we'll do all of our things in 2 dimensions and just know it just scales up the same. Okay, so we'll do random partition. So we'll just randomly assign. We'll say we're looking for 2 clusters. We're going to just randomly assign points to one of the 2 clusters. So I'm just sampling 1 and 2 with replacement for all of our things. And these are the assignments. So I have 3 points assigned to cluster 1, represented with black dots. And then I have 5 points assigned to cluster 2, represented with red dots. Okay? And that's fine. You don't have to end up with the same number of points when you do random assignments. Now, it is possible that when you do random assignment, like one of your clusters has like no points or something in it, then you just kind of re-roll. You have to re-roll your initial things. Okay. All right, so what we'll do is we'll take the points assigned to cluster 1 and assigned to cluster 2, and we'll calculate the mean of cluster 1 and the mean of cluster 2. So for cluster 1, we have the point 0, 0, 1, 1, and 4, 4. Okay, so the centroid of cluster 1, so 0, 0, 1, 1, and 4, 4, just kind of a coincidence that they're in a line here, will end up being, 0 plus 1 plus 4 adds up to 5 divided by 3. We get 1.667 for x1 and x2, 1.667. Okay, cluster 2, we have 0, 1, 1, 0, 3, 3, 3, 4, 4, 3. So we take the mean of those, all right? 0, 1, 3, 3, and 4 for x1, and we get 2.2. 1, 0, 3, 4, 4, 3, 4, 3, we get 2.2. Okay, so I'll graph these. Here I use dplyr to calculate the mean of cluster 1 and the mean of cluster 2. But I can plot those. So the mean of cluster 1 in black is this location, 1.67, 1.67. The mean of cluster 2 is 2.2, 2.2. And then now that we've calculated the centroids, we will reassign all of our dots to the closest centroid. So I'll go through all 8 dots, okay, and we'll say which centroid is the closest. So looking at this dot, so unfortunately the lines overlap each other, but we say, okay, which centroid is closer? Centroid 1 is closer. So we're going to assign this to cluster 1. Okay, what about this point? Which centroid is closer? Centroid 1 in black is closer, so we assign that to centroid 1. And then which one's closer? So, all 4 of these points, the centroid 1 is closer. Okay, and then we can also see, if we do for all 4 of these points, which one is closer, red or black, we're all gonna, we're gonna see all, for the red is gonna be the closer one for all of these, right? So we go through and we say which one is closer, and that one will get assigned to red. Okay, so these are the points after we reassign the point to the nearest centroid. And then now that we've done this, we will recalculate the centroid for each cluster. So I have 4 points assigned to cluster 1, 4 points assigned to cluster 2. We recalculate the centroid. All right, so what is the centroid of these 4 points? We will get 0.5, 0.5 right here. What's the centroid of these 4 points? We'll get 3.5, 3.5 right there. So here it is using dplyr to calculate that. We'll plot that, and then I guess technically we would go through and we'd say, okay, let's go through all 4 points. Which centroid is closer? And this centroid is closer. Which for all of these points, which close? And then so no points will get reassigned to a new cluster, right? So that would be an indication that we have reached convergence, and this would be our solution for our 2 clusters. Okay, and this was a very simple example, but it works. It works. Okay. All right. So here is another example. Here I generated 3 clusters of points. Okay. So so this is a little bit cheating because I I know the answers, but again, we're in unsupervised learning, so generally just data appears. But a lot of times there is some kind of process that create stuff and explain, like why some of these things end up being kind of similar to each other, right? And it's kind of like I don't know, how does like taxonomy work, where you look at I don't know, bugs or something, and you say, oh, this is like a new species, right? I don't know how it works. But at some point you're looking at a whole bunch of like specimens, and you say, okay, these are all very similar, and these are just different enough, and I don't know if they do, before even DNA analysis or whatever, like, they go, oh, this is different enough where, we're going to have like, this is an entirely new species or something, right? Versus, actually, I have no idea. I don't know how it works, right? So, because if I saw two different breeds of dogs, I might think they're like different species, but they're not. Well, anyway, so here we've got some points, and I know I've generated them from 3 clusters. But when they arrive, they're not we don't know which cluster they belong to or anything like that. And so we're going to just say, hey, let's see if we can assign these to some clusters. And so I'm going to just say, let's search for 3 clusters. Okay, so we'll start off with the answer, and we'll say, let's look for 3 clusters in our data. And with random assignment, I randomly assign them to clusters 1, 2, and 3. Cluster 1 is in black, cluster 2 is in red, and cluster 3 is in green. Okay. So I randomly assign these points to clusters 1, 2, or 3, just random assignment, and I'm going to calculate, what is the mean of cluster 1, what's the mean of cluster 2, what's the mean of cluster 3. Okay, and so it's just kind of like, because of randomness, the values end up being kind of just a little bit different, and the centroid for cluster 1 and the centroid for cluster 2 end up being very, very, very similar to each other. Okay. And cluster 2 centroid is plotted right above cluster 1 centroid, and see, there's just ever so slightly, I've got the black circle here and the red circle almost entirely covers the black circle, but there's just ever so slight difference between the centroid of cluster 1 and the centroid of cluster 2. Okay, so this is what we have, and we go through every point and we say, okay, which centroid is the closest. Okay, so if we take any point over here, it's going to look and it's going to say, okay, the red centroid is the closest. Basically, any point over here, the green centroid is the closest, cluster 3. And then there's only kind of like this small little sliver of points here where it's going to say centroid 1 in black will be the closest. Okay, so we go through and we reassign all of the points to the nearest centroid, and this ends up being the reassignment. So all of these ones say, okay, green's the closest, all of these ones, red is the closest, and just a small selection of points say the black centroid 1 is the closest right here. Okay, so now that we've reassigned all of the points, we're going to say, okay, all of the points, let's calculate the mean of all the green points. Let's calculate the mean of all the black points. Let's calculate the mean of all of the red points. Okay, we're going to calculate the centroids of each cluster now, of each group of points. And so, so you'll see on the next slide, the dots will move to the centers of each of these things. Okay, so the centroid of everything, all the dots in black is right here. The centroid of all the dots in green is right here. The centroid of all the dots in red is right here. Okay, and okay, so now that I've done this, we're gonna in the next step we will reassign all the points to the nearest centroid. Okay, so basically everything over here is still red. Okay, everything over here, green is the closest, and then now pull out my measuring stick. So we can look at, we have red and black here. I don't know, maybe, I don't know if this is even visible here, but you can kind of split the distance between, you draw kind of like a line that connects this, and then you'll pick like the midpoint here and do something perpendicular, and this will kind of be the boundary between red and black. Okay, and so everything over here, red is closer. Everything over here, black is going to be closer. Right? Same thing on this side. We draw a line that connects the black dot and the green dot, and then we pick halfway between, draw a perpendicular line, and this will be kind of the boundary between points that are closer to green, points that are closer to black. And so we'll reassign all the points to the nearest centroid. Okay, so I don't know if you can visualize those boundaries, and we do that, and that's what we get. Okay, and so now that we've reassigned points to the nearest centroid, now we're going to recalculate the centroid. Okay, so we'll say, okay, what's the center of all the red dots? What's the center of all the black dots? What's the center of all the green dots? Okay, and that's what we get, and then we repeat the process. Okay, and then so we say, okay, here is red and black. What's a line that is perpendicular and halfway between here? Probably right here. Same thing with black and green, and we'll probably draw a split right there. We reassign points, and that's what we get, and then we do a reassignment. So we've done the reassignment. Now we'll recalculate the centroids, and so now there's just a little bit of adjusting, okay? And then we reassign points, and then we do a recalculation, a little bit of adjusting, and then we reassign points, and nothing has changed, right? So now that I've calculated my centroids here, and I say, okay, let's reassign points to the nearest centroid, nothing changes. That's an indication that our values have converged. Okay, so that's what we have. The original data that I know, like I've cheated, and I know like the original data that generated this. So we would just normally just end here and say, okay, these are my clusters. I generated this thing, the data, so I know the answers, and the quote answers. Again, answers don't really exist, but we have this, and we say, okay, you know what? Some of these points are just ever so slightly different. Like this point in the original data came from, I guess, distribution 1, and this point came from the red distribution 2. But when we did our clustering, it said, this one's a little bit more similar to distribution 1 or cluster 1, and this point's a little bit more similar to cluster 2, and that kind of makes sense. But is it right or wrong? It's not. There's no, with unsupervised learning, there's no like right or wrong here. Okay. Okay. Let me give you your second view quiz answer, which is the letter B. B as in bear. B. Okay. Does that kind of make sense as far as how k-means clustering goes? So it's, again, this iterative thing where you alternate between reassigning points to clusters and then recalculating your centroids of each cluster. And we're using Euclidean distance, so there's pros and cons to that, and basically everything has to be, everything has to be a numeric variable. We don't have much way to get around that, at least for these clustering algorithms that use distance measures. There are other algorithms that might suggest different distance metrics, and we'll take a look at using a kernel function, kind of like when we did SVM, a kernel function. We can apply that to k-means clustering, and we'll do that on Friday. But and then you can use, like, rather than using centroids, you can use medians or medioids. There's little variations, little tweaks to the algorithm, but this is kind of the original, and it works. It works well. Okay. You can use there's a function called k-means in R, and it's quick and it works. but for your homework, I'm going to make you write your own little bit of code to do k-means clustering. But in real life, if you had to do k-means clustering, you'd probably just use k-means in R. But for your homework, I'm going to make you write a little bit. Now, one thing about cluster assignments is that who gets put into the label of which one is cluster 1, which one's cluster 2, and which one's cluster 3 is completely arbitrary. So there's no so here, in the center I have cluster 1, on the left I have cluster 2 in red, on the right I have cluster 3 in green. That's kind of what we had. And when I did my thing, I ended up like that. But here, when I did k-means clustering, cluster 1 in black ended up in the middle, cluster 2 in red ended up on the right, and cluster 3 in green ended up on the left. This is not wrong, okay? This is this is totally fine, and it's again which one you call A, B, or C is completely arbitrary. It's just like here's a cluster, and here's a cluster, and what's the order that you put them in. There's no kind of like set order, right? Okay, so that's k-means clustering, the k-means function in R. This command to do k-means clustering is very simple. You just do k-means, your data frame, and then you say how many clusters you're searching for. All right, and you'll get back a list with things. The cluster assignments are in results $ cluster, okay? And so here I can say, plot all of the data in our matrix, and we can do this, and that was the command to create this, okay? So I presented this algorithm of just kind of like, take your centroids, reassign your points, take your centroids and reassign your points. K-means clustering, we can also think of it as an optimization problem. What are we trying to optimize? We are trying to minimize kind of this quantity, which is the within group sum of squares. All right. So you could think of the within group sum of squares as here are the centroids. What is the distance from each dot to the centroid? And then you square that distance and you sum them up. Okay. And so if I go all the way back to say, I think it's very clear that putting a centroid here minimizes the within group squared distances, and putting the centroid over here minimizes the within group squared distances. Versus, what is the centroid of all the points? We might call that the grand centroid. If we put all the points, that would be right here, and we would have, a much greater kind of sum of squares there. Okay. So the within group is calculated as the sum of squared distances from each point to its own centroid, whereas the total sum of squares is the distances from each point to like the grand centroid. Okay, and then the total sum of squares is going to be equal to the within sum of squares plus the between sum of squares. So a lot like an ANOVA type of thing, where you have like within group variation and between group variation. You have that just in a higher dimensional setting. And so the algorithm that we have here often reaches some kind of solution of, or at least a local minimum for this optimization problem. The complete output of k-means is kind of this big list of the cluster assignments, a matrix of centroids. So here I have three rows because I've searched for 3 clusters, and then in 2 dimensions because I got an x1 and an x2, and so that's that. And then you have a few values kind of showing the performance of the k-means. You have the total sum of squares, the within group sum of squares for each of your three groups, or each of your k clusters here, and then the total of the within sum of squares, the sum of these three numbers, the between sum of squares, which is, if you take this, the between and the total within, it will add up to the total sum of squares. Also, just how many values got assigned to each cluster. Actually, I don't know what these last two things are. How many iterations? I don't think. Is that right? Only 2 iterations? I don't think that's right. Okay. I don't know what those last two things are. Okay. And here's kind of the, so here's the matrix of cluster means, the vector of assignments, and, with your within cluster sum of squares by cluster. What would happen if I tried using a different number of clusters? So if I did k equals 2, it will give me 2 centroids, all right? And these are my within cluster sum of squares. And it also gives you the ratio of the between sum of squares and the total sum of squares, which you can kind of think of as like almost like an R-squared measure. So, thinking back to ANOVA, you have like your model sum of squares or your between group sum of squares. So if you think of like one-way ANOVA, and if you haven't done one-way ANOVA yet, don't worry. But you have kind of like this R-squared value, which is this ratio between how much is explained by your model versus what's left over. And so we're going to say the between sum of squares is what's explained by the model. The within sum of squares is what's left over. And here we're saying this accounts for 86.2% of the total sum of squares, whereas using only 2 clusters accounts for about 70% of the total sum of squares. This would be what it looks like if we had 2 clusters, okay, which makes sense, I guess. That's that. If what would happen if I tried k equals 4? Okay. Let's take our data and I say look for 4 clusters. Okay. So if I do 4 clusters, here I did set seed 1. This is the results that it gets, and these are the 4 clusters it finds. Finds a cluster here, finds a cluster here, and then kind of these middle ones get split in 2. All right. The thing about looking for 4 clusters is that there's like more than one solution that converges. Okay. So if I run it again with a different set seed and I say search for 4 clusters, it has different random assignments in the beginning, and this ends up with a way. So this one, it split the center one kind of vertically, and here it's split the center one kind of horizontally. Okay, it still kind of finds this cluster over here and this cluster over here, and it splits this one horizontally. If I run it again, here's like another thing where it found 4 clusters. It said, okay, these are similar, and then as far as these points, it split this into kind of 2 groups here. Okay. And this is ultimately one of the difficulties of k-means clustering, is figuring out how many groups should you search for. Sometimes this is kind of an impossible task. The truth is whatever your data set is, you can always segment your data into a smaller subgroup, okay, that share kind of similar values. And you can say, okay, well, here's a group, and let's group them together. Just an analogy showing how kind of challenging picking a k is, what if I asked the question, how many racial or ethnic groups of people should we put on the census form? That's like such a very challenging, almost impossible task, right? Because you can say, well, so if you go back, decades, okay, I don't know what the census form looked like, but there was a time where, in the U.S. it would be like, okay, there's white versus non-white, okay? And then, you could further, or you could say, okay, we need more groups than that. Okay. And, and so, and, you might say, okay, well, you can have white, black or of African descent, Hispanic or Latino, Asian, I don't know, more groups. And then, if we take Asian as a group, that can further be split more, right? And you can have South Asian, East Asian, Southeast Asian. Any of those can be further split. So like if you take East Asian, that could be split into Chinese, Japanese, Korean, things like that. Any of those groups can be further split into more groups, right? And so it's kind of just like, well, when do we stop? When do we say we don't need to form any more subgroups, or this is enough? And it's kind of like, it's hard, all right? And so, depending on your data set, how many groups K should you search for, right? And if somebody says, okay, well, decide on we have room for 25 racial or ethnic groups on our census form, you probably won't find two people that will agree on exactly what 25 groups should be, right? And so it's really hard, okay? One thing you can do is you can try running the k-means clustering algorithm multiple times. And if your multiple runs kind of converge to the same clusters, then kind of this within group sum of squares will have no variation between different runs, okay? On the other hand, if you run it a bunch of times and each time you run it, you get different answers, that might be an indication that maybe this is not the right number of clusters. Now, it doesn't, even that said, even if you have like the quote right number of clusters, it's not necessarily going to result in things converging to the same solution every single time. So it's tough. Figuring out how many K to search for is a tough thing. And so, somebody who's kind of an expert or knowledgeable on the subject might, try to bring something in or something, okay, to give you some insight here. So here, I just ran a double, a nested loop, where one, I'm going to try, searching for K equal to 2 clusters, then K equal to 3 clusters, up to 10 different clusters. And then I just run k-means clustering 20 different times for each K, okay? And we'll just kind of look at the results. Each time I'm going to record the total within sum of squares. And so here it is with K equal to 2, 20 different times, and you can see the within sum of squares actually ends up being exactly the same all 20 times. And then same for K equal to 3, we get the same within sum of squares, total within sum of squares every single time. But then if I look at kind of the last few rows, when K equals 9, we get different within sum of squares. When K equals 10, we get different within sum of squares. And so here's kind of the average sum of squares and the standard deviation of the sum of squares. And so, as you increase the number of clusters, your within sum of squares will always kind of go down, right? You're always, it's like, okay, here's another subgroup that we found, and that's going to reduce kind of the within group sum of squares. That's a normal thing. How much, but then, there's variation between the within group sum of squares. When I have K equal to 4, we get different kind of clustering results. We saw some of those illustrated, and so we have some standard deviation. And so we can see with the different things, we get different, we get some variation here, right? I can kind of plot this. And so, going from 2 clusters to 3 clusters, results in kind of a huge drop in within group sum of squares. And then, as I increase the number of clusters to search for, the within group sum of squares does continue to go down, but we can also see there's quite a bit of variation, even among the solutions with, four clusters or something like that. So, with this, we'd probably look at it and say, okay, I think 3 clusters for this data set is good enough. But yeah, somebody could make an argument and say, hey, let's go for 6 clusters are here, and because I know within this thing, we can cluster this, and this kind of makes sense, okay? But it's, it's hard, right? If you think about like, okay, how many genres of movies exist? At the most top level, you have drama versus comedy, okay? But then, obviously there's a lot more stuff, and now, there's like action, and there's, and within each kind of thing, you have these subgenres, and you have these kind of like mixtures of genres, right? You have these comedy dramas, or I don't know, and as certain movies become more popular or whatever, now you have like a new genre of like just superhero, right? That's like an entirely new genre and things like that, right? So how do you cluster things, right? So you asked like Netflix, how do you decide like what shows to group together, and how to do it is hard, right? And you can cluster based on kind of things based on content, and you can say, okay, these are like movies and shows that feature similar kind of like sci-fi themes or similar like crime related themes. And then you can also just cluster things based on like non-content measures, like these ones have lots of views, right? And it'll just be like top 10 most viewed, right, this week or something. And that forms a cluster, right? So there's different kind of like things you can look at to kind of form clusters and form kind of groupings. So yeah, it's tricky, but it's an idea. Okay, so anyway, this just says, how do we pick our K? You can also, so we can run a thing. You can't do cross-validation. Why can't we do cross-validation?
There's no target values to calculate.
Yeah, so cross-validation requires target values, right? Cross-validation, you calculate how much error you have, and you can only do cross-validation for a supervised learning. For unsupervised learning, there's no like, okay, we got closer to the right answer for this thing than this other thing, because there's no answers in unsupervised learning. So no cross-validation, just, keep try running it multiple times and see if you get similar results. Okay, last view quiz answer today, keep the pattern going, will be the letter C. C as in cat is our last view quiz answer for today. Okay, we'll end here for today, and we'll see you on Friday.